students, and welcome! We're jumping right into Unit 3, Chemical Kinetics today. And we're going to tackle one of the most important ideas in this whole chapter, the rate of a chemical reaction. So, let's get started. So, have you ever really thought about this? You take a magnesium ribbon, you light it, and poof, it burns in a brilliant flash, just like that. But an iron nail, you leave it outside, and it takes months, even years, to rust completely. Now, both of them are chemical reactions, so what's the deal? Why is one super fast and the other incredibly slow? What is controlling this speed? Well, that's exactly what we're going to figure out. You might be thinking, okay, some are fast, some are slow, so what? Why do we care? Well, it matters a lot. If we can understand and control the speed of reactions, we can control some really important things. Think about making medicines, manufacturing products in industries, and even things in our daily life. It's a huge deal. So let's break it down to the simplest possible idea. What is reaction rate? It's just asking one question. How fast is our stuff, our reactants, getting used up? Or how fast is our new stuff, the products, being made? The most important part is that last bit. Per second, or per minute, or per hour. It's all about speed. Now let's zoom in, way in, to the molecular level, which we can't even see. What's really going on? Well, you have all these tiny reactant particles just zipping around, constantly bumping into each other. The reaction rate is basically us counting how many of those collisions are actually successful, the ones that manage to break old bonds and make new ones, in a certain amount of time. Okay, so we've got the basic feel for it. Now, let's get a little more formal. For your exams, you need a proper definition. So what exactly is the rate of a chemical reaction? Here it is. This is the definition you need to remember. The rate of a chemical reaction is the change in concentration of a reactant or a product per unit time. The two key phrases here are change in concentration and per unit time. It's about how much the concentration changes over a period of time. Now, this is a super common point of confusion, so listen up. There's a big difference between the total amount of product and the rate of formation. See, if your reaction makes 5 moles of product in the end, that's the total amount. But if it's being made at a speed of 0.02 moles every second, that's the rate. Rate always has a time component. Don't mix these two up. All right, if the idea is still a little bit abstract, don't worry. Let's use a very simple analogy to lock this concept in your mind. We'll call this the water drip analogy. Just imagine a water tap. If you have high water pressure, the water flows out really fast, right? Well, in our analogy, that water pressure is just like the concentration of reactants. And the speed of the water flow, the flow rate, that is our reaction rate. So it's simple. Higher pressure means a faster flow. Higher concentration means a faster reaction rate. See? Easy. So why did scientists even invent this concept? Well, think about it. They knew some reactions were like explosions and others were like rusting. But just saying fast or slow isn't very scientific. They needed a number. They needed a way to quantitatively measure and compare the speed. That's why the whole idea of reaction rate exists, to put a number on the speed of a reaction. Okay, that water analogy was pretty good. Now let's try another mental picture, a more detailed one, to really see what's happening at the molecular level. I want you to picture a busy marketplace. Now, if it's a slow day and there are very few vendors and shoppers around, not much business is going to happen, right? Things will be slow. That's exactly like a reaction with a low concentration. So in our market, who are the players? Well, the vendors, they are our reactant molecules. And what are they trading? They're exchanging chemical bonds. Every time a successful trade happens, that's a molecular transformation. A reactant has just turned into a product. So what is the reaction rate in our marketplace? It's simple. It's just the number of successful trades happening every single minute. And it makes sense, right? If the market is super crowded, high concentration, you're going to have way more trades happening per minute, a much higher reaction rate. All right, enough with the theory and analogies. Where do we actually see this stuff in the real world, in our everyday lives? Let's look at a few examples. Let's go back to our first example, the burning magnesium ribbon. Why is it so fast? Because when you heat it, the magnesium and oxygen molecules start moving like crazy, leading to an extremely high rate of successful collisions. The reactant gets used up in just a few seconds. That's a very, very high reaction rate in action. Now, Think about the fridge in your kitchen. Why do we use it? Because food spoils much slower inside. What's happening is that the low temperature inside the fridge dramatically slows down the rate of the chemical reactions that make food go bad. This is a perfect example of us using technology to control reaction rates.
And finally, here's a really interesting one. You learn in chemistry that hydrogen peroxide is unstable. So your first thought might be, okay, it should break down the second I open the bottle. But it doesn't, does it? It can sit on a shelf for a long time. That's because its rate of decomposition is actually extremely slow, unless you add a catalyst. So remember, unstable doesn't always mean fast.
Okay, we've covered a lot, so let's just quickly summarize the most important points that you absolutely must take away from this. Think of this as your cheat sheet for the exam. Here are the 3 things to remember. 1. The core idea. Rate is just the change in concentration per unit of time. Simple. 2. The mental image. Picture that busy marketplace. The rate is just the number of trades per minute. 3. The real-life example, your fridge. It works by slowing down the rate of spoilage reaction. If you can just keep these 3 simple points in your mind, the core definition, the marketplace picture, and the refrigerator example, I promise you, this entire topic will feel so much lighter and easier in your exams. You've totally got this.